which brings us to My Pi, or OMP, Deterministic AI Execution. OMP solves this stale file corruption problem natively. Like we just saw, standard coordinate-based diffs fail the second your code shifts mid-generation. OMP, on the other hand, utilizes hash-anchored edits, so instead of blindly looking for line 42, the system semantically locates the target code block based on its actual structure and content. If a developer shifts the code midterm, the tool instantly identifies the new semantic location and applies the patch perfectly. The secret engine making this happen is called hashline. It's a specific patching format that uses a 4-hex content hashtag to anchor edits. Think of it as a secure fingerprint for your code. Every single edit has to include this header tag for version binding, which completely eliminates whitespace battles and stale file corruption. If a file drifts between the read and edit commands, the edit is just safely replayed against a cached snapshot and securely merged. By identifying the code structure rather than its physical location, you completely prevent concurrent agent runs from clobbering each other. This represents a sheer architectural difference in how we handle automation. While most standard agents rely on fragile search and replace methods running on thin API wrappers, OMP brings out the heavy artillery. It runs a massive 27,000-line native Rust engine. This completely bypasses the overhead of spinning up external processes for critical tasks. Add in 32 built-in tools and direct language server protocol integration, and its edits become entirely symbol-aware, not just blind text replacement. And these aren't just theoretical benefits. We're seeing a rapid, real-world shift in the software industry right now. With over 300,000 monthly downloads and more than 26,000 GitHub stars, developers are actively migrating away from fragile coordinate-based tools toward this deterministic AI tooling. The fact that it natively integrates with over 40 AI providers proves that the enterprise demand for structurally sound automation is absolutely massive. Now, a crucial point is how this determinism scales up for large enterprise projects. OMP uses a first-class sub-agent architecture. Instead of one monolithic agent trying to do everything, a main agent delegates tasks out. Those sub-agents then run in parallel inside completely isolated work trees. They share zero memory, meaning they literally cannot accidentally conflict with one another. And when they finish, they don't return messy, unpredictable conversational text that you have to somehow parse. They return strict, schema-validated data. It's parallel execution combined with flawless state isolation. Because the core is so strictly organized, it unlocks a seriously powerful RPC mode. This means the agent can be controlled programmatically from any language or IDE via bidirectional JSON over standard input and output. You can run OMP entirely headless for CI/CD pipelines, integrate it directly into your editors using the agent client protocol, or even hook it up seamlessly to custom chat UIs, like WeChat bots. But with this level of autonomy comes very serious security reality. Unmediated, arbitrary bash execution and file writes are simply unacceptable enterprise risks. Having highly capable automated systems running wild, modifying code, and executing shell commands without guardrails is incredibly dangerous. Determinism isn't just about code accuracy, right? It's fundamentally about operational safety. OMP handles this exact risk natively through a built-in user consent mechanism called approval mode. By default, destructive actions like bash commands or arbitrary file writes trigger interactive UI confirmation prompts. In headless RPC modes, it just automatically blocks these calls to maintain total safety. You get fully configurable per-tool policies. Now, yes, if you absolutely want the agent to run free, there's an optional -- YOLO override frag. But the foundational architecture is built strictly on explicit consent. The hardware challenge here is immense. We are talking about code shadowing devices, meaning the firmware is loaded from flash memory directly into RAM for execution. Imagine you need to live patch one of these devices to fix a critical vulnerability, but you absolutely cannot trigger a reboot. If it's a drone mid-flight or a medical device sustaining life, downtime is simply unacceptable. The update has to happen flawlessly, in real time, without corrupting the live system. So how do you actually inject a patch into running memory without crashing the device? Kintsugi leverages a mechanism called the atomic context switch. This is a critical section within the real-time operating system scheduler. During this precise, tiny moment, saving and restoring a task's execution state is completely indivisible. If you inject the patch exactly during this specific window, the operation is guaranteed to be atomic. The system cannot be interrupted and the firmware state remains perfectly intact. To achieve this safely, Kintsugi maps out an end-to-end, highly secure deployment pipeline. First, a manager process handles the incoming hot patch.
Next, a guard component enforces strict access using the hardware's own memory protection unit, guaranteeing that attackers can't tamper with the patch while it's in transit. Finally, the applicator deploys the patch atomically during that exact context switch we just talked about. It is an incredibly tightly controlled, secure sequence. 38. That is the exact number of processor cycles this entire hardware application overhead introduces during normal operation. 38 cycles. To put that into perspective, that's roughly 0.59 microseconds on a standard ARM Cortex processor. That is literally less time than it takes a beam of light to travel 200 meters. It is practically invisible to the operating system. You get true enterprise-grade security and live patching with zero disruption to real-time performance.
Welcome to the deterministic future. The era of crossing our fingers and hoping a shell script runs cleanly or forcing device reboots from minor security patches is officially over. So I'll leave you with this to think about. Take a hard look at your own automation, your coding agents, and your update pipelines. Are you still relying on fragile coordinates and unpredictable scripts? Or are you ready to upgrade to semantic certainty and deterministic execution? Thanks for tuning into this explainer, and we'll see you in the next one.